we kind of finish up to one part. So let me recap what's going on so far. So what we have learned is that we have learned a bunch of key concepts that we will kind of work with throughout the course. The first thing is expanded decomposition, right? You have a graph, you find a set C that you delete, and then the node weighting become expanding after deleting. Yeah. And from expanded decomposition, we get something which I call repeated expanded decomposition. The picture is like this. Anyone can recall what it is, like what it does? Yeah, Lucas?
You keep doing expanded decompositions until you have, I guess, every edge is part of an expander, right?
Good. Yeah, right. You have a graph, you do expanded decomposition, you get a bunch of disjoint expander. Look at the cut edges, do expanded decomposition on that. So add and recurse. And then at some point it means that every edge will appear in some expanded component. And there will be just like log n many layers. And we have used this to get some application. Okay. The next object is separator expanding hierarchy, SE hierarchy. It's a hierarchy such that for each cluster, the separator is expanding. Okay. And we see how to construct this thing. Anyone recall what's the key object we used to build this?
Like the key data structure, or
the key object that once you can do it, then you can build this top down.
Oh, the zones, or the idle and the active zones, or?
No, that is like application of this thing. I mean, if I want to build this hierarchy, we see the algorithm to build this hierarchy. What's that?
Separator.
Yeah, exactly. It's a expanding balance separator, right? It's a separator, it's a set F here, the red thing, that is expanding in the graph. At the same time, it's a balance separator. If you can get this thing, then you can build this hierarchy easily. Just compute the expanding balance separator and recurse. And that expanding balance separator is just going to be your separator in the top level, and then you recurse on each component. Okay? Next, we learn about BSE hierarchy, which is just a strengthening of SE hierarchy, right? It's just the same thing, except that for each cluster, not just the separator is expanding. Its boundary is expanding too. Okay. Recall this? Okay. And just on Friday, we learned how to build this thing. Do you recall what is the technique we used to build this? Dynamic.
With the feed forward stuff. I don't remember the name.
Yeah, it's really dynamic version of expanded decomposition, right? You remember you can maintain expanded decomposition when you delete edges and when you increase node weighting. That's the dynamic version. And we kind of use this dynamic version to build this thing. Okay. And there's one lemma that we didn't prove. It's going to be in the homework. Okay. So, okay, good. Later in course, we're going to learn another construction, actually. It's going to be much simpler. The interaction is not as complicated as the one that we just learned, where you kind of have bottom up and top down interaction. This new one is going to be just bottom up, but it will have worse quality, not as good as what we learned, but it's fast. We learn this later. Okay. So this is like kind of the building blocks to build the key objects here. Okay. This is kind of the key objects that we're gonna use. Like that is really kind of the core to the theory. And once we have this thing, we have seen how to use, for example, repeated expanded decomposition to build edge specifier. We see how to use parallel linked version of expanded decomposition to build vertex specifier. And from this SE hierarchy, we see how to get the connectivity oracle under edge failure. Do you recall what is the application of BSE hierarchy? We get to build some kind of specifier. What's that? It's a super strong thing.
It's like the tree cut.
Yeah, the tree cut specifier. It's a tree flow or cut specifier. And like, if you look into this, like we actually see that from tree cut specifier, it can be used to build vertex specifier that is really like strong, like very small. Later in course, we will see how these two hierarchy can be used to build something called flow shortcuts. It's mainly for fast algorithms, so I didn't talk about it yet. But all these objects, hopefully you can appreciate it without even caring about fast algorithm. It's just some kind of graph compression that is useful. Okay. But all these things turns out to be useful for fast flow or cuts algorithm. Later we will try to build how to compute max flow fast. Yeah. So the red thing is like in the future that we learn. Okay. So that's the kind of the key thing so far. Like if you don't recall each of these keywords, record it. Okay. Okay. So the next phase of this class is to kind of, once we learn these key objects, and we have kind of ignore how to build this thing fast so far, we're gonna now try to build these objects fast. Okay. And in the first next 2 weeks or something, we're gonna get all this thing basically in almost linear time. So really fast, really useful. But what we're gonna assume is that we can solve max flow in almost linear time too. So we assume some powerful black box. We know now that max flow can be solved in almost linear time, and we're gonna assume this, and we're gonna build algorithm that is fast for building all these things. Okay. But later you see that these tools itself is gonna be useful to build fast max flow algorithm too. Like it's like kind of it's a chicken and egg dependency. And later we would try to obtain how to find how to solve max flow fast too. Yeah. I don't think in this course we will see how to find max flow, how to compute max flow in almost linear time. That requires quite a complicated algorithms, but you'll see how to do this in n squared time, which is basically still near linear when the graph is dense, right? So it's still really good, and yeah, okay. So to get to fast algorithm, we're gonna learn first about cut matching game. Cut matching game is like the foundation of how to make all this thing fast. So it's basically the the framework to compute this thing fast. And once you compute this thing fast, you can compute this thing fast and the application later. Okay? So that's what we're gonna learn today, this thing. Okay. Any questions about like what's going on in the class? Okay, good. So what is cut matching game? Okay. Okay. So the way you should think about cut matching game is that it is one way to construct an expander. So I have kind of mentioned several ways to construct expanders. Expander, you can build it easily if you can have many edges. For example, just build a clique. That is clear expander. Okay. But if you want it to be sparse, then now that's not clear because it has small number of edges, yet you kind of want the graph to be well connected. Okay. But there are ways to do it. One way is just to take random graph. So that's easy. Just put like maybe a random graph with n log n edges. That's gonna be expander, like with like the cut expansion is gonna be constant even. Okay. There are like explicit construction, so not randomized, it's deterministic. And you can look at hypercube or some other algebraic construction that you can come up with, like that people have came up with. But okay, this thing is something that like is a kind of construction that you choose how to build it. Okay, and cut matching game is another kind of way to build low degree expander. It's a way to build an expander under adversarial environment. So there are some adversary that will try to construct the graph, and you kind of force this adversary to build an expander for you. So that's what cut matching game is. So from the first glance, if this is what cut matching game, then it's not so clear to you yet that why it's useful for fast algorithm. We learn this maybe in next class or next week. Okay. So now let me describe the game. Okay. So the game is that there were gonna be two players, a cut player and matching player. Okay. And initially there's gonna be just empty graph, G0, where you have an empty graph G0 with vertex V and no edge. Okay. Good. And what we're gonna do first is that like in each round, the cut player will play first, and then the matching player will play. That's gonna be turn. Like for each round, what cut player will do, it will choose disjoint set A and B. Okay. So originally people say that you need to choose cut, like A and B that partition the graph into two, but we will not require that actually. We can be more flexible. We can just say that A and B are disjoint, okay, and A is of size less than B. So that's what cut player will do. Then the matching player, what it will do is that it will choose a matching between A and B. And the matching will need to match everything in A. So the matching will match if there are like 4 nodes here and 6 nodes here. or more than 4. Then the meshing will just mesh every node in AI to some node in BI. Okay. So the cut player don't know what choice of MI will be. Like the cut player just choose AI BI, and the meshing player will mesh everything in AI. And you can mesh everything in AI, right? Because AI is less than BI. Okay. Okay. So again, a reminder: a meshing is just it's just a disjoint set of edge, right? This meshing edge don't share endpoints. Okay. That's the meshing. Okay. So once the meshing choose MI, then we're just gonna kind of include MI into your graph. So the graph at time GI consists of the meshing from round 1 up to round I. That's what GI is. Okay. So the graph will keep growing. You keep putting the meshing into it. And basically, the game will finish whenever this node wedding unit vector, like all one vector, is expanding in the graph. Yeah.
The node weighting just it's kind of like the indicator node weighting is just every node is 1? Or?
Yeah, every node is 1. This is 1V is when every node has weight 1. Yeah.
Also, does that matching player, does he just choose arbitrarily, we assume? So kind of at random?
Yeah. Think of matching player as adversarial. So he tried to choose a matching so that the graph doesn't become expander, like try to delay the process as much as possible. Okay. Yeah.
The edges in the matching, can they be already in the graph, or does it have to be new edge?
If there were edge from U to V already, if you you could add like a parallel edge from U to V again.
Oh, like multi-edge.
Yeah, you can have multi-edge in this graph. Okay. So that's the game. So what's the goal of the two player, right? Cut player try to build expander, try to make the all one vector to be expanding in the graph in the fewest number of rounds. Okay. So you want the graph to be expander as fast as possible. The cut player. Okay. So the goal of the cut player is to cleverly choose a cut that kind of force the graph to be expanding. No matter what the matching player do. Okay, does. Then yeah. So that's the goal of the cut player. Choose cut nicely so that the graph become expander. And the goal of matching player is just to add some arbitrary adversarial matching. And his goal is to delay the process.
Can the cut player see like the matching player?
Yes, that's important. The cut player can see what is the graph so far. Okay. So the agenda today is that we're gonna think of ourselves as a cut player. We're gonna design a cut player strategy so that no matter what the matching player does, you're gonna get the graph will become expander in like log square rounds. So quite quick, very quick. Yeah. So if it takes like just K round to finish, at the end of the K round, the max degree of every node is at most K, right? Because the matching is a graph with degree 1, max degree 1. and it's a union of K matching, so the graph has max degree K. So if you can finish this within few number of rounds, so you get like low degree graph such that like it's still an expander. So that's good. Okay. And once you see this thing, once you get like a cut player that is like good, then in later class we will assume this strong cut player that we design today. And then we're gonna design the matching player. And by designing both cut, like once you have good interaction between cut player and matching player, you see that you're gonna get nice algorithm out of it. That's how we get fast algorithm, fast expanded decomposition and so on. You can get this by like designing how cut player and matching player interact. Okay. But forget that today. Today, just focus on cut player, how to choose AI/BI nicely.
For the cut player, so they want to minimize the number of rounds or the number of edges.
Number of rounds. Yeah. Okay. So because if you just want to minimize number of edges, then you could just, for example, choose like AI/BI to be like just one, just singleton and singleton here, and the matching player has no choice but to add one specific edge. So you have full control, but it takes many rounds. But you want to minimize the number of rounds. Okay. Later we're gonna use this to build all these things fast. Yeah. Okay. So now let's think about some heuristic. Okay. Suppose that you wanna solve this problem. You are a cut player. Okay. What would you do? Okay. So first, how would you choose AI and BI? First, you want AI and BI to be balanced in the sense that they are big. Because if they are big, then you add many edges. So that should be good, right? Like if you just AI and BI has small size, then you have more rounds. So AI and BI should be big. Okay. What would be your next suggestion? What AI and BI should be? How should it look like? So suppose that the graph so far looks like this maybe. This is the graph G, I-1. How would you choose A and B? Yeah.
Go ahead, sorry.
Okay, yeah. Okay.
So I got it, yeah. I guess components, this kind of components.
Yeah,
right?
you can choose the two components like this, right? Then like at least it connect the two components together. Okay. What about like if the graph look like this is already expander here, and this is another expander here, like well connected, but this is still connected, but there is a sparse cut here. What would you do? Still kind of choose A to be one side here, B to be on one side here, because there is just this sparse cut, and we don't want sparse cut. We want the all one vector to be expanding. So if there is a sparse cut, just choose that cut. At least it fixes that cut, right? Like once you choose this, then like there will be kind of a meshing crossing this thing. Then now this is not sparse anymore. You agree, right? This is like really intuitive. So you want AI and BI to be balanced. At the same time, you kind of want to fix sparse cut. So then the idea is just to find balanced sparse cut. And then like whenever there is no sparse cuts left, we would be done. So, okay, so first it should be balanced. Next, maybe it should be sparse cut. Or because MI, the matching that cross AI and BI would fix such a sparse cut. So this is kind of, the idea is that because once there's no sparse cut left, we are done. By the way, like what if the graphs look like this? Yeah, like no. This is a graph and this is already well expanding. This is expanding, but this is not of size n, but it's of size root n. Then if you just still choose some cut like this, that contains, as long as A contains a sparse cut, it's going to be fine too. Because you know that the matching edge that you add, everyone here will add some edge crossing to another side. So as long as AI contains a sparse cut, the sparse cut that AI contains will be fixed, will not be sparse anymore, right? Because all these guys will have some edge outside of this set to even not just complement of the component, but to somewhere else, like far away. That's, yeah. Okay. So does it make sense to you that this heuristic really is intuitive? Just choose balanced sparse cut. Okay. So in the homework, you show that this works. Yeah. And it will finish even after log n rounds. Okay. You can say that there's no balance, there is no sparse cut left, and then all one vector would be expanding. So the problem with this approach is just that kind of the real goal of building this cut matching game is to find sparse cut fast. We kind of build, the whole point of building this game is for the application of doing expanded decomposition or to find sparse cut fast. But it turns out that the strategy to solve this is to find balanced sparse cut. So it's kind of solving the problem that we want to. It requires a solution where we want to solve as an application. So that's not so great. Okay. So what we're going to do today is to get another algorithm. We're going to describe another algorithm that is clearly fast. It's just near linear time. And it will not ask you to find balanced sparse cut. It's just do something else. Okay. Okay. So that's the goal. Yeah. So what we want to do is that we want to show another algorithm, choose AIBI, such that at the end, the all-one vector is maybe flow expanding. Okay. In some way, in some clever way. And I will fix one thing. Okay. Before I present you how to choose AIBI, we will look at some process that I call round robin walk. Okay. So why do we talk about this? Before I describe it, let me tell you a bit. So the whole goal right now is to choose cuts. Sometimes I call cuts, but it's not really a cut. It's just AI and BI might not be like partition, but like just disjoint set. Okay, but I call this cuts too, because yeah, it's just easier to talk about. Okay, so we want to choose the cuts AIBI so that at the end, maybe like the all one vector is flow expanding. Okay. So to prove this, to prove that something is flow expanding, it means that you kind of need to construct. It means that you need to construct a flow that route the product demand, right? That's the definition of what it means to be flow expanding. If you can route the product demand, then you're done. Okay. If you want to construct a flow that you can route the product with demand with low congestion. Okay. So means that right now you kind of need to choose cuts cleverly, and also kind of show how to construct a flow that route this demand. Okay. So from now, I'm just gonna fix how I construct the flow, so that our choice just left on how to choose the cuts. Okay. And this process is gonna be simple, very structured and easy to analyze, and it will always give the flow with congestion 1. It will route some demand with congestion 1, but it might not route the product demand yet. Okay, and so the goal is to, what we're gonna need to do is just to prove that this process route the product demand of all one vector at the end, like maybe with some scaling. Okay. So, okay. Okay. If it route this, then it would be 1/4 or 1/2 flow expanding. Okay. So that's kind of the motivation. Let me tell you what is this process. It's called round-robin walk. Okay. Maybe let me tell you what this process is first. It's a process where, let's say you have a graph, and let's say the starting point is at V0. Okay. It will do this random process where at route I, okay, it will just look whether, maybe it starts from route 1. At route 1, it just look if V0 is matched by M1. So there is going to be matching in M1, maybe like this. Okay. If this is M1, if V0 is not matched by M1, then you're gonna just stay put at V0. Because, so at route I, we just look at the matching MI. So if M1 doesn't match V0, then we don't do anything. But if V0 is matched by M1, then there's going to be 2 choices. Okay. With probability half, we're just going to stay put again, just stay at the same point. With probability probability half, we're going to move from V0 to V1. This is just where V1 is just the mesh edge. Okay. And then you look at the next round. The next round, there's going to be maybe just look at maybe M2 is here. Okay. This is M2. In the next round, you just check if it's supposed that you are at this point, you just again check if you are matched by M2 or not. If you are not matched by M2, you just stay there. And if you are matched, then you go to the next to your mesh. You walk through the matching edge with probability half, basically. So we call it round robin because in round I, we only use edges from MI to walk. If there is an edge that is an MI that match you, then you go there, like you go along the matching with probability half. Is this process clear? Yeah.
The first case where we just stay put vi equals vi minus 1, we just in the next step we'll still look at the same node.
Yeah, yeah.
Just keep looking basically until we walk or
Just keep, like, so here just mean like we I equals vi minus 1 here. It's just stay put. And then in the next round, you just look at the next matching. If it's now if there is match, if you are matched by the next matching, then you walk along the matching with probability half. Yeah.
Right now we are fixing all the MI and we are trying to find the flow.
Say again.
So we are fixing all the MI and then we're trying to find a flow in the final graph.
Yeah, this kind of once if MI are all fixed, then this process kind of defines some flow, right? Like yeah, I get to that soon. Yeah. But I hope that this round robin walk is clear. Okay. So from now I guess just gonna denote PI UV to be the probability that that the random walk above, when you start at node U, and it will end at node V after I round, after I steps. This is just probability that you follow this, like do this process for I rounds, and you start at U and you end at V. Okay. And once you have this, then you can define a matrix PI, which is just kind of collecting all, like for every pairs, this is PI is just a matrix 0, 1, 0, 1, V times V, right? Where the UV entry of PI is just PI UV. Okay. So what's the PI at time 0? It's just all 1. Like it's just identity, sorry. Right? Because it just means that if you start at U, the probability that you go to any node is 0 except if V is U. Okay. Does it make sense that P0 is just identity? Okay. Okay. So now here's a claim. Think of PI here as a matrix. It's not going to be symmetric, by the way. It's not going to be symmetric. For example, if, for example, maybe this is U, this is U1, U2, U3, okay. And M1, this is in M1, and this is in M2. Okay. Then P2 of U1, U3 is going to be what? 1/4, right? Like you're going to walk from here to here with probability 1/4 because at round I, you're going to go here with probability half, and at round 2, you're going to go here with probability half. Okay, what's P2 of U3, U1?
Zero.
It's 0. Because at round 1, you cannot walk anywhere. And at route 2, you're gonna walk to here with probability half. So you cannot even reach U1. Make sense? This is 0. Okay. So it's not symmetric, but it's just some matrix. So, but now think of this PI as a symmetric demand. Like it's just like we have been talking about symmetric demand so far, but now think of this as a symmetric demand, where like it's just set at like from some node U and V, you want to send flow from U to V by how much? By PI of that entry. You can think of this as a demand. Okay? And the claim is that when you look at PI as a demand, this demand is routable in GI with congestion 1. Okay. So let's see this. Like, actually, before I go to the proof, at least does the statement make sense? You don't need to see why, but yeah.
The congestion is 1 because the entries are probabilities, so we have the kind of demand is at most 1 in the matrix, or?
So every entry is between 0 and 1 for sure, but that doesn't imply that the congestion must be 1. For example, when you have this graph, right? And let's say I want to route between, like, if I want to route, like, if my demand is between 0 and 1, but it's just between, but still, I want to route many demand between these two sides, the congestion on this edge is going to be really huge. Okay. So, yeah, it's true that this is between 0 and 1, but this is still non-trivial.
So demand here is not symmetric.
Not symmetric. Yeah.
So like, but we've been talking about only symmetric demand.
Yeah.
So like that's what we learned still apply.
Like I just gonna construct some directed flow
Oh, okay.
that route this directed demand with congestion 1. But the concept kind of generalize easily, yeah, when you talk about asymmetric demand. Okay. So more question about the statement itself before we go to the proof. Okay. So to see this, imagine like let's say we're gonna prove by induction. Okay. That is P0 is routable in G0 with congestion 1. Okay. And P0 is routable in G0 with congestion 1. That's clear. So P0 like look like what? So this is, so you think of this as like a column at node A. Okay? A column of P at node A. This is a column at node A. Okay. Which is just to say that like, so this is kind of, this is like the mass at, the mass that end up at A. Like so this is like, this is for A, this is for B, this is for C, this is for D. Okay. This is like the probability mass that start at A and end at A after time 0. This is the this is just, so this is just P0 AB. So the probability mass that start at A, no, sorry. This is column, so probability mass that start at B, it's like probability mass from B that go to A at time 0. So this is 0. This is like P0 CA, P0 DA. Okay. So in the beginning, you can see that so you can think of this vector as kind of the distribution from everywhere, like the probability mass from everywhere, how it end up at A. That's this vector. Okay. And in the beginning, everyone just have like elementary unit vector. Okay. And this demand is clear that you can route. You don't need to route here. You just you can route it with congestion 1 in empty graph because you don't need to do anything. Okay. So now let's look at route 1. Okay. Suppose that in route 1 there is matching mi, and let's say matching mi just contain one edge like this. Okay. Mi contains one edge like this. So what would happen to the probability mass, like the distribution at B and D? Okay, so you know that any particle that start at B, if there is a matching edge here, it's just gonna go to D with probability half. So like this thing gonna stay put here with probability half, and it's just gonna move to this. It's gonna move to D, and you get probability half here. Okay, and this thing from D too, it's just gonna go to B with probability half. So this the probability mass that start at D, yeah, it's just gonna stay here with probability half and go to B with probability half. So that's why this will become 1/2 and this become 1/2 because it moved from here. So that's why like after this edge, after this round, the probability mass, like the distribution at B looks like this, and at D looks like this. Actually, they're gonna be the same. They're gonna be the same because it's like you kind of basically average them. Okay. And let's look how much flow has been, like if you think of probability mass as flow, how this mass move, the total flow that moved from B to D is just going to be 1/2, because basically 1/2 of this thing moved down, and 1/2 of this thing move up, 1/2 and 1/2 move down. So 1/2 here move down, 1/2 move up. So the total flow or probability mass that go through this is exactly just 1 unit. Okay. So, okay. So what does it mean so far? It means that I can route P1. This is my P1. P1 is just by putting all this vector together. Right? P1 is like a demand. And we just route this P1 demand with just congestion 1, just by sending flow along this edge. Okay, so we get the first route works. Okay. Yeah.
So are we allowing multi-edges in like the final G?
Yeah, we allow multi-edges.
I guess I don't see why this isn't just like pretty. I guess I don't see why it isn't trivial then, because at each step we have at most one at any point, and we only send like half of that.
Exactly. That's the proof. That's the idea of the proof. Exactly. Yeah. Okay. Let me still goes on give another I just want to make it really concrete so that you can imagine what's going on. Okay. So suppose that my next matching is this thing, these two guys. Okay. So what will happen? So let's look at this guy, right? What will happen is again, half of this vector will go here, and half of this vector will go here. Because you can think at B there are a mix of particles starting at B and starting at D, but you can think any particle that end at B will just move to A with probability half. So you can think just say that half of the vector here will move to this, and half of the vector here will move to this. Meaning that now what P2 of A will look like is just that half, it's just going to be half of its original mass, plus half of the vector from B. Do you agree with this? And the same for B. P2 of B is just exactly the same thing. Because half of the mass at round 1 will stay at B, and half the mass from A will come to B. So just from looking at this, you can see that they are the same. You just so what happened is really that when you look at the vector, the two vector, you just update them by taking the average of the two vectors. So now they become the same. Yeah.
I have a question.
Yeah.
Now let's say we have two matches in like this, but then let's say you had a match from A to B and A to C.
Right, but that is not a matching. A matching cannot share a node.
Okay.
Okay. Yeah. I allow this kind of matching. This is a matching, but this is not a matching. So yeah. So matching is a set of disjoint vertex, disjoint edge. So what happened here is the same, right? Why the vectors at C and D looks like this? You just average the vector at C and D from the previous round. Okay. And if you look at, so that's how you can see that's how the vector is updated. And if you look at how much probability mass go through this edge, it's really just going to be 1/2 from this side to this side, and 1/2 from this side to this side. It's really because it actually doesn't really matter what's the specific number here. This is just the sum of this is 1. And half of them will move to another side. Sum of this is 1, half of them will move to another side. So the total flow through this edge is 1. And so far we just see that this process kind of define a flow that route P2 in G2 with congestion 1. Like this edge is not used here, and congestion here is 1. In this route, only edges in M2 is used. Congestion of this is 1 too. So every edge has congestion 1. Okay. So from this illustration, I hope you can see that at route I, vertices exchange mass only through Mi, and and also note that the total mass on every node is always 1, because you see like it start like with the total mass 1, and then like you exchange some mass, and the total mass is always 1. Yeah. The way to see this is just the total mass here is 1, the total mass here is 1, and you update it by either like stay the same or average of 2 vectors with total mass 1. So, okay. So the total mass at every node is always 1. And you can see that the congestion, like the congestion is 1 because the total mass that goes through edges in Mi is exactly 1. Just 1/2 in one direction and another half in the opposite direction. Okay. And once you route through an edge in Mi, in route I, you will not use it again. So the congestion stay 1 on that edge. Okay. Also, like I hope you see that this process route this demand Pi. Like the mass distribution that end at A, at vertex A at the end, is precisely the column Pi at the column A. Okay. And I hope that this illustration just shows it. So are you convinced that at route I, like how the mass distributes just look like Pi? So this means that we basically route Pi. Okay. If you really want to be more convinced, like let's see how the process really induce multi-commodity flow that routes Pi. So let's see like this figure below. I will just kind of show this how this random walk after I step. That let's say we focus only on the flow that's starting at B. After I step, it will generate 2 to the I flow path starting at B. Okay. So like here it starts with empty path, and after route I, there's gonna be 2 paths, this path and just this empty path here. This path will have flow 2 and like 1/2, and this path is 1/2. And then the next round, like you're gonna stay here with 1/2 and go with along the meshing here with 1/2 probability. So it induces a flow with 1/4 value here, and this edge here, this flow path is kind of split into 2. This guy with 1/4 and go here with 1/4. So you see, right, that like this process after I step, it will generate 2 to the I flow path starting at each node. So by combining this flow path all together, it just gives you the flow that routes the Pi demand with congestion 1. Okay, so I hope you are convinced that that this round-robin walk will give you this. Okay. It will route some demand Pi in GI with congestion 1. So if we can force PI to be like a product demand, then we would be done. It would like, if PI here is like product demand for all one vectors, then it means that we successfully route the product demand with low congestion. So now the goal is like try to choose cuts so that PI evolve to become product demand. Okay. Okay. Okay, so here is a strategy. Okay. Here's really the main theorem. What we're gonna do is like we're gonna choose, like in each round we're gonna choose AIBI in time something like NI, and there's gonna be just log square rounds. So and at the end of log square rounds, the PI that we route is gonna look like product demand of this R1 vector. So which means that R1 vector here will be flow expanding. So the total running time is gonna look like this. There are, the time that you spend is Ni, there are log square rounds, so the time is like log to the 4th. Okay. So, okay. So now, how do we approach this problem? How do we force PI to become something like product demand? Okay. So from now, I want you to think geometrically. Okay. So think of this column of A as like n-dimensional vector. This is like r to the n. And think of this as the position of point A, of node A in n-dimensional vector. Right? So now like think like each node is on the space, n-dimensional space. Okay. And the average of all points will look exactly like R1 over N. Okay. R1 vector over N. Okay. And my potential function is really going to be the length from, like the distance from point A to the average square, summing over all nodes. Okay. So think like you have points, and then there is some average. This average will be R1 vector over N. And what I'm going to measure is like the distance to this R1, distance to average square. Okay. So why this is good? So the point is that suppose that my potential function is 0. Then I claim that we are done. When the potential function is zero, it means that PI, like the point at A, is just R1 vector. So it means that like if this is 0, if this is 0, the potential is 0, it means that this thing is just R1 for all U and V. It's just 1 over N for all U and V. Which just means that PI is just a product demand. And we are done. Okay, so that's why like we kind of want to reduce the potential as much as possible. When this is small, then we are done. So if this is 0, then we are really done. And note that like in the beginning, the potential is something like n. You can think like this is like at most 1, for example, and it's sum over 1 n times, so it's just at most n, but it's going to be exactly n minus 1, and the potential is at least 0. So we see that if the potential is small, is 0, then we are done. But I claim that if the potential is small enough, not quite 0, but just polynomially small, then we are done too. Then we like IV would be like flow expanding. So why is that? Because this potential, right? You can just write it like, instead of summing over all nodes, you can sum over all pairs of nodes. And this is just Pi of BA minus 1 over n square. Right? Because this norm square is just, right? It's just B P AB, this thing, square. This is just 2 norm, 2 norm square. If there's nothing here, then it would be this. But I square it, so okay. So then you get this thing. Okay. But this whole thing is small. It's smaller than this. So it means that individually, each of this term is less than this thing. So when you take square root from both sides, you get this thing. So it just means that for every pair UV, it deviates from 1 over n by at most 1/2 over n. Which just means that Pi is at least 1 over 2n on every entry. And recall that the product demand of all 1 vectors is just it's just the demand where everything is 1 over n. And what you know is that like now you can so it means that here Pi is at least the product demand over 2, right? But Pi can be routed in GI with congestion 1. So you basically can route product demand over 2 with congestion 1. So you can route the product demand with congestion 2. If you can route the product demand with congestion 2, then the flow expansion is 1 over 2. Okay. So I hope that you are convinced that now. Yeah.
Could you explain where the 1 over 4n squared comes from? Like, how did we make that argument?
Okay, so I want this to be like, I want this to be small enough because once this is small, it means that individually on each term, this is small. What does it mean for this to be small? It means that this guy deviates from 1 over n by something small. So basically, it just means like this is close to 1 over n if this is small enough. And once I just set this to be something like 1 over n square or 4n square, it means that this thing deviates from 1 over n by at most square root of this. I just take square root from both sides.
But we just assume that it's less than or equal to 1/4n squared, or?
Yeah. We assume this. Like we assume that if the potential here is less than 1/4n squared.
So then later we can make the argument.
Yeah. So now it shifts the goal now to just minimize this potential. Okay. So now the goal is like you want to minimize this potential to be polynomially small. Something like 1/n squared. Or we can do it 1/n to the 100. Doesn't matter. We can do that easily. So once the potential is small, like 1/n squared, then we are done. And we want to do this, achieve this within a few rounds. Okay. And what does it mean to make this small? It means that we want to move every point to be close to the average. Right? What does it mean for this to be small? This is the point A. We want this to be close to the average. Okay. So now let me motivate the algorithm. Okay. So again, let's think geometrically, right? Think like Pi of A is the position, like the column of A of Pi is the position of A at time I. Initially, at time 0, each point is like kind of at the corner of, it's just elementary vector. It's like 1 here and all 0, 1 here and all 0, and so on. Okay. So it's kind of far away from all 1 vector. It's kind of at the corner of the simplex. But you don't need to know the word. It's just this thing. Yeah. And we want to move all of them to be close to like all 1/n vector. We want to move them to this thing. Okay. And you see that after we choose AI and BI, the meshing the meshing player will return us some meshing MI. Okay. And the way that the points move is like this. If A is not meshed, then it stay put. The distribution, the position of A will not change at all. Right? The position stay the same. And if A is meshed to some node B, then we really just gonna move the position of A and B. If this is position of A, position of B, what will happen is just the position will be moved to the average. Okay. So if we could just like choose endpoints and say that everyone should move to the average, we would be done in one go. But right now we just kind of just say that the meshing player will basically average a bunch of pairs for us. Okay. Yeah, we average each mesh pairs. Okay. So for example, let's say this is like a point. Okay. The good choice of A and B can be like this. Like if they are kind of clustered that are far away from each other, and we kind of want everyone to be kind of at the center here. If we choose A and B like this, then after meshing, the meshing will mesh somehow. I don't know how they mesh, but at least each of these pairs will kind of come close to this thing. I can choose a choice like this too. That's okay. Can you tell me what's the bad choice? Give me some example of bad choice. Yeah.
Like if you were to do like, instead of doing this like vertical split, do like a horizontal split on that example.
Yeah, horizontal split. Because if the meshing player is really generous for us, then it might mesh like this. And that's good, but but the matching player can be adversarial, and it could just match like this. And now, like, okay, they move a bit, but they're still far from the average. And another choice that is bad is like, even if you choose some guys that are far away, but it's not big, then you just make progress only on one pair. That's not good. So in general, we want AI and BI that is large, and they are well separated. So this kind of really match the heuristic that we discussed in the beginning. AI and BI should be large. And when they are well separated in this geometric sense, it really kind of means that there are some sparse cut between them. Why? Because the reason that they are kind of far away from each other, kind of well separated, is because there has not been like probability mass that move between them. So there must be some sparse cut that prevent this thing from moving. Okay, but you can try to convince yourself that this corresponds to sparse cut. Yeah. So it really matched the heuristic that we have. Okay. So basically, if there is some points like this, we kind of want to choose a cut that, like, if there are some points that are well separated like this, you kind of want to choose this A and B here to make them come close together. So that for every vertex A and B, let's say this is A, this is B. For every pair here, for any arbitrary pair, the distance, the pairwise distance between every pair in A and B are big. Okay? So they will come close together. And for any matching edge, we'll reduce the potential by a lot, no matter what, if that's the case. Okay? So that's the intuition, what we want to do. But let me tell you, like, how can we hope to do this fast at all? Right now, we think geometrically, and but like this matrix Pi, each node is every node is in n-dimensional space. Like, so the matrix Pi is like half of size n square. Okay. So we don't even have the time to write down what is this matrix Pi. We don't have the time to see where is the point, where is the position of each node. Okay. So the key idea is to use dimension reduction. Okay. So what we're gonna do next time is that we're gonna basically choose some random direction. And then project every point into this random direction, meaning that you think like you have some dimensional points in high dimensional space, right? And then I just choose one direction R, and every one just gonna be mapped to this point, to this direction. This really kind of reduce, like once you project every point to this line, it reduces the dimension from n to 1. Okay, so at least, so this, if this is point A, then, and this is R, if I project it to x of A, it just means like I project this point to R, which is really just inner product. So the projected point of each node A is like inner product with of the point to this the direction R. And the position of every node here will have like takes just one number. So this vector is just takes n numbers. So at least if we hope to work with this projected points, then there are just n numbers instead of n square. We can hope to make it fast. By never explicitly working with the points in n-dimensional space, but work with the projected points. Okay.
But you can have like very far points and project to very close to
Very good. Yeah. So why this should work? Like there can be some very far point and then they project it to something very close. It's like when you project something, you lose information, right? You really reduce information from n dimension to 1. Here's the point. Why should this work? We're gonna choose random direction. Once you choose this random direction, then the random projection will preserve square distance with good probability. We're gonna show this formally, and this is like the message that I want you to at least remember if you forget about card matching game. This is used a lot in TCS. So some vertices will the distance between some vertices, some pair of nodes will not be preserved, but with good probability, most pair will be preserved. Okay, so basically this is, and what is preserved is really not a distance but square distance. So this is basically kind of why we define our potential function to be based on square distance. Like the intuition so far is just we want to measure distance to average. This could be norm 2, norm square, or norm cube, or whatever. But because random projection preserves square distance, so that's why we choose square distance here. Okay. So if the square distance is preserved, when you start with this kind of points in n dimension, when you project, it's just gonna look like this is R, and now it looks like this. Suppose that they really preserve distance. And once you have this line, you just it's kind of easy to find the cut. Just kind of choose something in the middle, or choose something that kind of, it's easy to look, like once everything is on the line, it's kind of easy. Yeah, you kind of detect where you should cut easily. So that's what we're gonna do. So far, I hope I motivate the algorithm, and next time we will see how we do this formally. Okay, so yeah, that's it for today. Tomorrow Thursday we see the algorithm. It's just this simple. Right. Okay, see you.